Welcome back, everybody. In this video, we're going to continue working on section 3.3, which is about measures of relative standing and then also box plots. So where we left off was we were considering the idea that if a data value is more than 2 standard deviations above the mean or more than 2 standard deviations below the mean, then we could consider that significant. So that's shown basically in this illustration here. Values within 2 standard deviations of the mean on either side we would consider not significant, and then values that are, of course, outside that interval, either on the low side or the high side, would be considered significant, either significantly low or significantly high, depending on which side of the arrow we are on. So as an example, I want to take a look at number 12 from our textbook. The story goes, in the process of designing aircraft seats, it was found that men have hip breadths with a mean of 36.6 centimeters and a standard deviation of 2.5 centimeters. And then we have a source. We're to identify the hip breadths of men that are significantly low or significantly high. So that means that we want to know what lengths in centimeters would correspond to 2 standard deviations above or 2 standard deviations below the mean. So this is a little different from examples we've done before, which was to basically, given data values, come up with z-scores. Now we basically are trying to go the other direction. Since the boundary between what's significant and what isn't significant is 2 standard deviations, we want to know what lengths in centimeters correspond to those lengths or those differences in terms of numbers of standard deviations. All right, so let's start with the left end. So -2, we're looking for the x value that would be 2 standard deviations below the mean. So we'll say that's x minus, and then our mean is 36.6 centimeters. The standard deviation was 2.5 centimeters. So what we're using here is the z-score formula. Z is x minus mu over sigma. And the way that we were using this formula before was we were given an x value and then mu and sigma, which we had to have. We were given x, mu, and sigma, and we calculated a z-score. What's different on this one is, of course, again, we're given mu and sigma, but we want to know x, and we're given the z is -2. So we're going to use a little bit of algebra and solve that for x. So first we'll multiply both sides by our decimal, 2.5. This is where basically your algebra prerequisite is going to come in handy. So now we're going to add 36.6 to both sides. Okay, and then this will give us our x. So x is equal to 31.6. Okay, so that's on the low end. So we're going to basically replicate that now for the higher end. All right, so going through similar calculations for the +2 standard deviations, we can find out that our cutoffs basically would be at 31.6 centimeters and 41.6 centimeters. That's in terms of x values, and that's in centimeters. In terms of standard deviations, that's z, and they were -2 and 2. So why would you care about such information? Well, what we found out is that most hip breadths are in this interval, 31.6 to 41.6 centimeters. And this would have some bearing on how we might choose to design an airplane. We want to make it so that it fits most people, but then we don't want to make it so big because we would like to be able to fit in more seats and sell more seats to more passengers. So that kind of a discussion would necessitate our knowing how big the passengers are. So we saw with the empirical rule that assuming that these values are normally distributed, about 95% of males have hip breadths in this interval between 31.6 and 41.6 centimeters. All right, so here's another example. This one's kind of long, so take your time to read it. It says in the 87th Academy Awards, Eddie Redmayne won for Best Actor at the age of 33, and Julianne Moore won for the Best Actress at the age of 54. For all Best Actors, the mean age is 44.1 years, and the standard deviation is 8.9 years. For all Best Actresses, the mean age is 36.2, and the standard deviation is 11.5 years. And then there's some fine print about the ages, and then relative to their genders, who had the more extreme age when winning the Oscar, Eddie or Julianne? And then we're going to explain. So we want to calculate z-scores for both people. And so we'll go with Eddie first because he's the first one mentioned in the problem. And so I need a z-score for both people. So z is x minus mu over sigma. And then his age was 33. For all Best Actors, the mean is 44.1. And then standard deviation is 8.9 years. So he was younger than average. They didn't ask us who was older. They asked us who had the more extreme age. So he is about 1.25 standard deviations below the mean. So now we'll make the same calculation for Julianne. So her age when she won was 54, and the mean for women was 36.2 with a standard deviation of 11.5. All right, so that's interesting by itself. You'll notice that the Best Actress winners have a higher standard deviation than for males. So that suggests they're more variable, which in a way is not that surprising. Okay, so 1.55 for Julianne. So his was below the mean, hers was above the mean, but that question here is asking us who had the more extreme age, which would be further from the mean. So I would say hers is more extreme based on our calculations. Okay. Another example, it says in recent years, scores on the MCAT had a mean of 25.2 with a standard deviation of 6.4. We're going to identify the MCAT scores that are significantly high or significantly low. So as with our earlier example, we're going to basically find the test scores that would correspond to z-scores of plus and minus 2. So you should pause the video, try that, and then see if you get the same thing that we do. All right, so I've gone through the calculations here, and for a z-score of -2, again going through the algebra here, for a z-score of -2, we would end up with a x value of 12.4. I've set up our x minus x bar, or our x minus mu over sigma formula, and I went through the algebra steps to solve for our score. And then for a z of +2, same basic formula, solved that for x and got 38. So the cutoffs corresponding to plus or minus 2 standard deviations would be 12.4 and 38. So we want to know the scores that are significantly low or significantly high. So ones on the low end would be below 12.4. And then the high side would be above 38. Okay, so that answers our question. All right, so moving on next to the idea of percentiles. So we've seen z-score as a way of describing relative position of values within a data set. Another way of doing it is by using what are called fractiles in general, and one particular type is percentiles. So percentiles, as I said, are one type of quantiles or fractiles, which partition data into groups with roughly the same number of values in each group. So percentiles, as the name kind of implies, are where we divide the data into 100 groups. So they are measures of location denoted P1, P2, all the way up to P99 and so on. That divided a set of data into 100 groups so that about 1% of the data is within each group. So it turns out that the median that we'd looked at before divided a data set into halves, right? Half the data was above the median, half the data was below the median. By dividing it in half, right? That was the median. So the idea of percentile is basically the same idea, only instead of cutting our set of data into 2 pieces, we're cutting it into 100 pieces. Percentiles are used often when there's a really large data set. For example, our class, it wouldn't make very much sense for me to divide your scores up into percentiles because there's not that many of you. There's definitely less than 100, right? So it doesn't make sense to do 100 subdivisions. On the other hand, if we were giving some sort of a test nationwide, like the SAT, or we were measuring people's heights at a certain age, where there's thousands and thousands of people that we're considering, or the lifetimes of brake shoes that are installed in certain types of cars where there's again thousands, percentiles might be useful. But for relatively small data sets, percentiles are kind of overkill. All right, so that said, we want to see how we can work with percentiles. I do have this nice example actually that we'll see first. If you have children or were one at some point, right? You've been to a pediatrician's office or a doctor's office, they have this chart that measures basically how quickly you're supposed to be growing, I guess. There's one for boys and one for girls, and it measures basically the height and weight as functions of time from birth to 36 months. And so I want to show you how to read the chart because it's kind of interesting in and of itself, and it is an example of the use of percentiles. Okay, so the structure of the chart first is that there's overall 2 sets of bands. There's one for weight and one for length. I guess when you're a baby, you're laying down more, so they go with length instead of height, okay? So there's length and weight, okay? Also, everything is in both metric and US units, which is why for weight you see both kilograms and pounds, and then for length you see both centimeters and inches. Those are the vertical scales, okay? The scales in 2 parts. There's a scale one towards the bottom, a weight scale towards the bottom, and a length scale towards the top. Horizontal axis is age in months from birth up to 36 months. And each heavy line that you see in the graph is 3 months worth reading across. Okay, so then how to read the chart. Let's say that you have a child that is 12 months old. Okay, so 12 months is right here. The first set of bands is for length. Okay, that's the upper set of bands. So then right here, circled in blue, that would be kind of the important values for a 12-month-old. So following the curves across and upward, you'll see that there's this set of numbers corresponding to each band, 5, 10, 25, 150, 75, 90, and then 95. Those are percentiles, and that's why we're discussing this right now, is because they are percentiles. They are basically, if you divide up all of the girls who are, for this one, 12 months old, into 100 categories according to their lengths. This is what they're saying the 5th, 10th, 25th, 50th, 75th, 90th, and 95th percentile are as far as length. So we'll take the middle first. Right there, that is the 50th percentile. So they're saying that a 12-month-old, 50%, so half, will be around 29 inches long. Okay, the really long ones, the 95th percentile will be around 31. The shorter ones, around 27. Okay, so each of these bands corresponds to a percentile. The middle heavy line is the median, or 50th percentile, and then we have the 5th and 95th percentiles as the upper and lower bounds of this band. Okay, so for weights, let's go with down here for weights. Let's say you have a 6-month-old this time. So 6 months is here. Okay, the 5th percentile, let me actually go one with younger because otherwise it's going to be split across 2 different sets of legends. Unfortunately, let's go with a 3-month-old instead. Okay, so for a 3-month-old, in terms of weight, the low end for pounds would be around 9 3/4 pounds. The 95th percentile is about 14 1/4 pounds. And then the 50th percentile is about 12 pounds, it looks like. So that's how, if you've done this before with your kid, they say, okay, well, they're on track or not on track as far as the rate at which they are growing. So by comparison to their peers, more or less. So that's how the chart works. Not that we need it directly for this class. I just wanted to show this because it's interesting and it's a nice application of percentiles. We can get a little bit more out of it too. That would be kind of fun as well. So 2 things that we can ask or see if you can think about. You'll notice that both sets of bands start out relatively close together and spread out as they grow upward. Both sets of bands start out narrow and then spread out. Okay, so think for a minute, why do you think that they would do that? Okay, so one reason I can think of that they would do that is this is a scale from birth to like 3 years old, right? When babies are born, they're more the same, right? There's less variability in like the length of a baby, right? Which is what this says. Okay, they're 95% of them range between 18 and about 21 inches in length, right? Most of them do. By the time they've gotten 3 years old, a lot more factors of come into play, how well they eat and things like that. Heredity starts mattering more when they're older, and that's why there's more variability among the older ones. Okay, in both the weight and in the length. All right, so that is enough of that. Like I said, that was the girl chart. If you want, you could look on the internet for the boy chart. Okay, so what we want to look at next is how do you find out percentiles? So if you have a set of data, how would you find out what the percentile is? Okay, and so there's a formula for that. The formula goes like this. We take how many values there are that are less than whatever data value you're looking at, divide by the total number of values there are, and that makes a fraction. And then we're just going to turn that into a percentage by multiplying by 100%. So here's an example. Suppose that we're looking at these cell phone airport data speeds in megabits per second from Sprint. And so they range from 0.2 megabits per second up to 30.4 megabits per second. We want to know the percentile. We're going to do number 18 down here. What would be the percentile corresponding to 13 megabits per second? Okay, so while we could figure out the standard deviation and calculate a z-score and stuff like that, that would be a good way to measure the relative position of 13 megabits per second. Another way to do it is to say, okay, well, this is what its percentile is. Okay, so how we're going to do that? There are how many values smaller than it? How many values altogether are there? So there's 5 rows and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values in each row. So there are a total of 50 values. And then we want to know where is 13 megabits per second and how many values are less than that. So 13 megabits per second is right here. So we want to know how many values are smaller than that. So there were 50 altogether. So there's 49, 48, 47, 46, 45, 44 are smaller than 13 megabits per second. And so that is 88%. Okay, so then that means that the 13 megabits per second is in the 88th percentile. Knowing something is in the 88th percentile is useful in that we can picture, okay, let's say that we had 100 of these data values. That means that 88 of them would be smaller than our particular value. Okay, so again, how do you find a percentile given a data value? You divide the number of values smaller than the one you're looking at, divided by how many total values there are, and then make a percentage out of it. Okay, going the other direction. Okay, this way, or this takes a bit more work than what we just did. What we were just doing was saying, okay, I've got this data value, I want to know its percentile. What we're doing now is, okay, I know a percentile, what data value would have that percentile? Like for that megabits per second one a minute ago, we saw that 13 megabits per second was at the 88th percentile. Let's say I asked you what value was at the 70th percentile. How many megabits per second is that? That's what this procedure helps you with. Okay, finding a value at a given percentile. So given the percentile, how do you get the value? There's kind of a long flow chart for this, and then we're going to try it down here with an example. So we're going to do it actually a couple of times for a couple of different kinds of values. So we want to find the value at the 88th percentile. And the data that we're looking at for this is durations in seconds of 24 eruptions of this geyser in Yellowstone. They range between 110 seconds up to 273 seconds. Okay, so let's try. We want to find the value at the 88th percentile. What that means is if we were counting eruptions for a long time and we had a whole bunch of them and we want to know what time would correspond to having 88% of eruptions shorter than that time. All right, so here's how. So start. Sort the data. The data needs to be in order for you to do this procedure, really. Okay, so our data is already in order, luckily, so that's good. Sorry for making you dizzy. Data is in order. Now we're going to calculate something. It says calculate capital L, which is K over 100 times N, where N is the number of values and K is the percentile in question. So let's try. So L is K over 100 times N. So K is the percentile in question. So here this is 88th percentile. And N is the number of values. How many values we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24 values. Okay, so 88th percentile, so 88 over 100. And then that's multiplied by how many values you have. So that's 21.12. Okay, that's the end of this green block. Now we're up to this decision block. This diamond shape is a decision block. And it says, is L a whole number? 21.12, was that a whole number? Yes or no? Okay, no, it's not. So we're going to go down here. Change L by rounding it up to the next larger whole number. Notice it says round up, not round to the nearest. So we're going to round up. 21.12, we're going to round that up to 22. Okay, just following the directions in the flowchart. The value of PK, what was K again? K is the percentile in question. So P88 is the L value counting from the lowest. L is 22, so we're going to find the 22nd value. I know there are 24 values here. There's 24, 23, 22. That's 266. That's the number at the 88th percentile. Just to recap what we did, we took the percentile that we wanted, like 88 or whatever, the 88th percentile, so 88 divided by 100 times how many numbers you have. Was it a fraction or was it a whole number? It was a whole number, or it was a fraction. So we turned it into a whole number by rounding up. Always round up in this context. And the number we want is that number in our list. So it was the 22nd number, so that turned out to be 266. Okay, all right, so now let's try that again. We want to find the value at the 25th percentile. So back to the beginning of our flowchart, data is still sorted. Compute our L. L is K over 100 times N. This time we're doing the 25th percentile. That's 25 over 100. And that's times 24 values. And that's going to be 6. Okay, back to our decision box. Is L a whole number? This time it is. So we're going to go across. Yes. The value of the kth percentile, 25th percentile here, is midway between the Lth value, that is 6 here, and the next one. Okay, so it came out an even number this time, or a whole number this time, so it was 6. So let's look in our data values for the 6th number. 1, 2, 3, 4, 5, 6. So the 6th one is that 234. It says the value of the kth percentile is midway between that one and the next one. So basically take the mean of that number and the next. So it's 234.5. That's midway between 234 and 235. So there's this kind of longer process to find the value at a certain percentile. You calculate this value, L, that we're interested in, as the percentile divided by 100 times how many numbers there are. And then you check and see if it's a whole number. If it's not, you round up and use that number. If it is a whole number, you use the mean of that number and the next number in your list. Okay, so that has been our look at percentiles. Another commonly occurring fractile that is in use is quartiles. And as the name there implies, that's where we divide our data into fourths. Like there are 4 quarters in a dollar, so and 4 quarts in a gallon. So quartiles divide the data into fourths. Okay, and there are 3 of them: Q1, Q2, and Q3. So you want to not let that trick you first. If you think about it, if we're dividing something into fourths, we've got to cut it 3 times. Okay. I know often people will think, okay, quartile, there should be a Q1, 2, 3, and 4. But no, let's say that you've got your birthday cake, happy birthday. You're going to cut it into 4 pieces. If you cut it into 4 pieces, you've got to cut 3 times. Okay? So Q1, Q2, and Q3. Okay, Q1, which is the first quartile, separates the bottom 25% from the upper 75%. Q2 is the second quartile. It's the same as the median. It separates the upper 50% of the data from the lower 50% of the data. And then Q3, the third quartile, separates the bottom 75% from the upper 25%. Okay, so how you calculate this is you use that percentile procedure that we'd had before, using the 25th, 50th, or 75th percentile. So that flow chart that we'd had, you can use that to help you calculate percentiles, and use, calculate using that L formula with 25, 50, or 75. Frequently, when we're doing this by hand, our data sets are small enough that we can just look and we're going to find out. So let's try it on this one data set here. So let me see how many numbers there are. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Luckily for us, there are 12 data values. So let me first divide that in half. 1, 2, 3, 4, 5, 6. So there should be 6 above and 6 below. And then each half, we're going to divide in half again. So there's 12 numbers. If we divide them into quartiles, it makes sense, should make sense that there are 3 numbers in each group. So for Q1, Q1 is going to be 5. Q3 is going to be 9. And then Q2, which is the same as the median, will be 6.5. Okay. All right, let's try that again. So you should pause the video, try this, and then see what you get, see if you get the same thing I do. So I'd start by counting the numbers. This time there are 15. So that 7 should be the middle one. Let me just make sure. If there are 15, there should be half as many, half above and half below. Looks like I missed. Try that again. 1, 2, 3, 4, 5, 6, 7 below, and 7 above. All right, so Q2 is this 7, and then Q1 will be the basically the median of this lower half. So there are 1, 2, 3, 4, 5, 6, 7 numbers below. So this 4 will be Q1, is the middle of our lower half. And then for the upper half, 1, 2, 3, 4, 5, 6, 7 numbers. That 11 will be our Q3, the median of the upper half. Okay, so like percentiles, quartiles can give us a sense of basically roughly where is a quarter of the data on the upper end and on the lower end. All right, so that takes us to the end of this video on percentiles and quartiles, essentially. In the next part, we're not quite done yet. In the next part, we're going to look at box plots and a little bit about outliers. So let me know if you have any questions, and have a great day.